Welcome to the office. We want to take a look at Theorem 21.9, of course, section 21 here. And I'm going to give a proof of this theorem, but I want you to know that if you choose not to watch the entire video, I would completely understand. This one is going to open up GeoGebra, so it might be really helpful if you have been experiencing difficulties there. Maybe you'll see a little bit, but otherwise, right, we grab onto our theorem. If you want to watch the proof, that would be fantastic. It's a little bit longer. And I don't have all the details perfectly aligned between what I know it's supposed to be and what I'm going to present right now. So anyway, so the altitude concurrence theorem. The three altitudes of a triangle are concurrent at a point called the orthocenter. Orthocenter. Excellent. And we want to give a proof. Now, the space that's provided here is actually not enough. So what we're going to do is we're going to use another piece of paper, several pieces of paper here, but then we're also going to use GeoGebra. So I'm going to go ahead and open up, let's see, open up my web browser here, and we are going to go to GeoGebra, geogebra.org. And if I've been opening this up in any previous videos, they're a little bit older, you may have noticed, so it looks a little bit different. So I want to, in this case, simply start the calculator. It didn't give me the options. The previous design of the website had the different calculators that you could do. If you're not already on geometry, up here you can select which one you want. So, and you may be interested in opening up more than one screen, as I believe is the case for the activities that you just completed, or the computer explorations rather. So, okay, geometry is what I want here. And we're talking about the concurrence of the altitudes. So what I would like to do is I'd like to create a triangle, create the altitudes, and then take a look at some line segments. And that's going to take a little bit here because we're going to create a lot of stuff. So to start us off, we can use our basic tools. I can create some points. So I can pick up 3 points, A, B, C, and everybody's happy. Things are good. Then I can create a polygon from these points. I can click on the points A, B, C, and close it back at A. So we have triangle ABC, and I would like to create the altitudes. So the altitudes are perpendicular. So for the point through, sorry, the line through B, the altitude through B is perpendicular to AC. So the altitude is the line that gives the height from the base, essentially, right? That's the idea. So I would like to create that. But when I look over here, if I want to create a line, okay, pick a point here, and then, oh, what about here? Ooh, you don't want to do that, right? It's not about there. You have to figure out what exactly the perpendicular through B is. So let's do that here. I'm going to Control Z, get rid of that line. And then to get more options, I'm just going to hit more. So this allows me to find the perpendicular line. I can find the line that is perpendicular to AC, which passes through B, and now I have the actual line that I'm interested in. Okay, so I'm interested in the concurrence of this line, along with the one that's perpendicular to that through C, and perpendicular to this through A. And what's really awesome, again, you've been experiencing this a little bit. Oops, I didn't want that. Escape a couple times there. I can select my points and move them around, and so we can get our intersections, or the intersection that we're going to prove occurs in different places. So let's throw it right there for no particular reason, but we very nicely observed that we can move it around. All right, this is what we have in our theorem for a triangle. Its altitudes, 1, 2, 3 altitudes are concurrent. They intersect right there. And now I want to prove that indeed what we see here is the case. And I'm going to do that through the construction of several lines, creating a new triangle. So I'm going to do that by constructing the parallels of each line through the opposite angle. So I want to create a parallel line. So I want a line parallel to this through here. a line parallel to this through here, and a line parallel to this through here. So now we have this huge mess of lines that is happening. And so what I'm going to do is I'm going to change the colors a little bit here. Oh, that's not what I want. I'm trying to simply move things around. Move. Here we go. I've created a new triangle, and the triangle that I want is of the parallels. So not these altitudes. So I am going to, let's see here, find some intersection points so I can look at a new triangle. And when I look here, there's no option for points, right? I can edit, construct, measure, lines, circles, polygons, transform. There's no option for points, finding an intersection point. So I actually need to hit more one more time, and now I have points, and I can find intersection points. So I want to look at the intersection points of the parallels. So the parallel through C, right, parallel to this side, that line, and the parallel to this through B, boom, that gives me intersection point D. All right, so I did these two, and now let's do this one and did this one. Let's go that one through this. There we go. And then finally, we want the parallel to this, which is that guy, and the parallel to this. Excellent. So we have this triangle, and we want to then consider the triangle F or DEF. All right. If I want to see this a little bit more clearly, what I'm going to do is I'm going to add some new line segments to create our new triangle. So let's create another polygon. Oh, let's see here. Circles, polygons. Here we go. Polygon, and I'm going to go D, E, F, and back to D here. So we have two polygons. And what I'm going to do at this point is I'm going to go ahead and do some show and hide. So select objects to hide. I want to hide that parallel. I want to hide that parallel, and I want to hide the other parallel. So now once I hit escape, they're all gone. So I've created this new triangle using parallels. Oh my word. All right, these are the things that I need for my proof here. With these parallels, I can observe that this line and this line are parallel because, right, that's what we constructed are parallels, and this line are parallel. So ACBF is a parallelogram. Similarly, ACDB is a parallelogram. And that idea, right, because it's a parallelogram, FB is the same length as AC. Similarly, BD is the same length as AC, and therefore we get the equivalent distance of FB and BD. So B is the midpoint of FD. Yay! Remember now that this line was constructed as the perpendicular to AC, which means it's also perpendicular to FD. So this line is the perpendicular bisector for this larger triangle on that side. Similarly, skipping all the details of congruent of congruent line segments, right, from our parallelograms. So similarly, we can find that this line is the perpendicular bisector of ED, and that this line is the perpendicular bisector of FE. So we have three perpendicular bisectors for the larger triangle. At that point, we have by the perpendicular concurrence of perpendicular bisectors theorem, which is already proven or whatever, right? It may be an exercise or proven a little bit later, but it's a theorem we've already passed. So we already have that tool in our pocket to be able to use. So a concurrence of perpendicular bisectors gives us that these three lines are indeed concurrent. Boom, we know that they are concurrent. Done, right? And that's it, because these are the same lines as the altitudes of the original triangle. So that's the idea. That is all of what we want for the proof. And what I'm going to do now is I'm going to simply write down everything that we just said. So if you've been watching and you're like, wow, satisfactory, I know what's going on, I'd like to be done. Great. Thank you for watching. Have a great day. If you would like to see the nice format of the proof, please continue to watch. So we are going to work through this. Zoom in a little bit here. So I've got my nice piece of paper and we are writing a proof. The first thing, the things that we are given is that we are given a triangle ABC, which indeed we have. Triangle ABC. Fantastic. So that thing is given. Continuing our two column proofs here. The next thing that we did was we actually constructed the altitudes of the triangle. We constructed the altitude right perpendicular to AC through B, the perpendicular to CB through A, and the perpendicular through AB, sorry, perpendicular to AB through C. So we created those three. So let's see here. We want to, let's see here. Perpendicular. My apologies. I'm trying to decide what we want to do for naming points here or naming lines. Let's create some lines. So let's go struct measure line. Basic tools. Yeah, that's fine. So we want the line. Oh, we want the line AC. Now that's giving it everywhere. We want the line CB. Now it's going everywhere. The line AB. That goes everywhere. So that's going to give us a few new points that we can identify and name. So that would be really good for us. And I overlooked the intersection somewhere along in here. Points intersect. Here we are. The intersection of the this line is the altitude. This line represents the other side, so that gives us G. And we have the altitude passing through A, perpendicular to this side, and then we have the perpendicular, the altitude, so through B, through A, through C. So we want to look at this altitude, and we don't need the extension of that side necessarily, so there we go. In fact, this line right here, oh boy, that's not what I want. This line right here, we don't actually. Okay. I do want, oh, it deleted that point though. So I do want, oh, will it let me observe that intersection? Yeah, okay. It gives me that intersection one. All right. With those in hand, we can construct our perpendiculars. That is our altitudes. So perpendicular to AC through B, let GB be perpendicular to AC. So we have let GB make that a line, be perpendicular to AC. That was a line segment, although the overall line. And we want, let's see, through B. Let's go through C. So CI, let CI be perpendicular to BA. And AH perpendicular to BC. Excellent. And this is given by the perpendicular existence theorem. All right, so we constructed our perpendiculars. So that's not what I wanted. Now what I want to do is with those perpendiculars, I want to show that they intersect. Fantastic. We have we want to now we want to construct the parallels so that way we can talk about this new triangle. So let's see here. Parallels. So we are going to name them. So for this line here, I want to select objects. I want to see its name. Oh no, that's not what I wanted to see. I don't need to see that one. Parallels are the ones that I want to see, and that one doesn't have a name because I hid them. All right. Let's let FD be I. So as a note here, I'm just going to put this in red so we remember FD. I guess not I. We'll go with L. Just to help us remember FD. Let's call FE M. So that's the line. We're saying that these are essentially names. And then FD, FE, ED. We'll call N. So this will allow us to construct or to refer to the parallel lines at this point. So we can construct the parallels. We want to let, see, L we said was FD. FD, so let L be parallel to AC through B. Let L be parallel to L is parallel to AC through B. Excellent. M is parallel to FE is parallel to BC through A. And then N must be parallel to a B through C. And this is given by the parallel existence theorem. All right. It's going to take a little while. We got this. So we have our parallels constructed in our proof. All right. Now what we want is, see, we give the existence, and now we want to give intersections. Yeah, okay. So we know that since this and this are parallel and this are parallel, then since these two intersect, then this one and this one are going to intersect, right? So by the transitivity of parallels, okay, they're not parallels. These, right, this and this are not parallel, so this and this are not parallel is the transitivity that we're using. That will give us that they intersect. So we get each of the sides intersecting. So we get, let's see here, L and M intersect at, we already have the label pointed, so L is FD, M is FE, so they intersect at F. M and N intersect at L and N have D in common, so that's D, and then, oh, I'm sorry, that was M and N. M and N have E in common. And then L and N intersect at L and N have D in common. There we go. And again, this is the transitivity of parallels theorem. Excellent. So at this point, we have a triangle FED. Fantastic. All right. Now we want to point out, again, not quite right there. Now we want to point out that this altitude, which was perpendicular to AC, must also be perpendicular to FD. Okay, so BG is perpendicular to FD. Yep. BG perpendicular to FD. BG perpendicular to FD. BG there, not BC. Okay. BG is perpendicular to FD. We also have that, let's see here, the one through B, the one through C, CI is perpendicular to ED. CI is perpendicular to ED. That was the one through C. The one through A was AH. AH is perpendicular to FE. And this is from the converse of the perpendiculars, or the parallel perpendiculars corollary. So what do we have so far? Well, at this point, we have big triangle FED, and we have perpendiculars, right, which were the altitudes BG, AH, and CI. Okay, so we have perpendiculars to the sides. Now, if we can show that they are the perpendicular bisectors, then we're all set. Whew. Okay. Now, we want to identify our three parallelograms. AFBC is a parallelogram. So 6, that was AFBC is parallelogram. AFBC. Excellent. We also have that ABCE is a parallelogram. AFBC. What I said there, ABC. Oh, ABCE. Yep. Okay. Yep. That makes sense. And then I need ABDC. Is a parallelogram. And these are all by the definition of a parallelogram. We get it because we constructed parallel sides, right? The line FD is parallel to AC, therefore FB is parallel to AC and so on, right? All right. So we get several parallelograms, and now with the parallelograms, we can go ahead and use the fact that they're parallelograms. It gives us that FB is congruent to AC, or that their distances are the same by our understanding of congruence, I'm sorry. And then AC is, has the same measurement as BD, therefore FB is the same as BD, and so on. So that's what we want to use here. So there are several things that we want to use. So I'm going to try to give them in the order that makes sense. So I'm going to give us, let's see here. 2, 4, 6. They're showing, see, this is the same as that. Oh yeah, we'll start there. We'll start with FB is the same as BD, and then try to avoid repeats. So FB is equal to AC. Let's see, make sure I got plenty of room here. Yep. All right, so 7 FB is equal to AC. AC is equal to BD. And that gets us that FB is equal to BD by the transitivity of equality. Excellent. So the other one that we want is, well, let's just go with this side next. So we have that EA is the same as CB. EA is equal to CB. EA is the same as CB, and CB is the same as AF. CB, AF. That gets us EA is equal to AF. Okay, so we got this side, we got this side, so that's just this side. All right, by parallelogram, we get AB is equal to EC, AB, EC. AB is equal to EC, and we get that AB is equal to CD. AB equal to CD. Fantastic. If you don't recall, that is this idea of parallelogram giving us the equality of the side length. That's actually due to a theorem, right? Not the definition of a parallelogram. So that's theorem 17.3 in particular, part B is what gives us that. All right, now we can finally get the equalities that we wanted, right? FB is equal to BD. FB is equal to BD. EA is equal to AF. And AC is equal to CD. And this is by the transitivity of equality. All right, so we're getting there. Where else do we need to go from that? Okay, that established that this is a midpoint, this is a midpoint, and this is a midpoint. So we can say that. So step 9 here. A is the midpoint of EF. B is the midpoint of FD. And C is the midpoint of DE. And this is simply by the definition of a midpoint. Fantastic. All right. So we have midpoints, and then we have that these things are perpendicular. So we're pretty much done. We just need to make that connection. We've established perpendicular, we've established midpoint. Therefore, by the definition of perpendicular bisector, we have a perpendicular bisector. So BG is the perpendicular bisector of FD. BG is perpendicular bisector. Is line segment, or the whole thing rather. BG is perpendicular bisector of the line segment FD. All right, so then CI is the perpendicular bisector of DE. I'm sorry, CE is not correct there. DE, I believe, is what we were looking for. DE, yep. And then, let's see here, AH is the perpendicular bisector of EF. AH is the perpendicular bisector of EF. And this is simply by the definition of a perpendicular bisector. Fantastic. We're pretty much done. At this point, we can conclude that the desired lines BG, CI, and AH are concurrent. We know that they are, right? Those are the altitudes that we drew. So those are the altitudes that we drew, BG, AH, CI. Those are concurrent because of the concurrence of perpendicular bisectors. So perpendicular bisector concurrence theorem. And we already have proven that, so we can use it. Boom. All right, or it's one of the things to be proven in your exercises or whatever the case may be. Or I guess we will prove it, but it's a passed theorem is the point. We've already passed it, we've already assumed it's true, and so we're moving on. All right, that is the proof. So it took a little bit more than just the one page. That's why we wrote it here instead of on our notes here. And we used, again, GeoGebra to help us out. So if you've stuck it out and watched the whole thing, congratulations, you made it to the end. Fantastic work. Have a wonderful day. There's certainly more to say from this section. So I'll see you guys back in the office in a little bit.